It is a pleasure to welcome you to the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP lecture series is an pro bono initiative led by Dr. Pfaffhuber Mr and Professor Andreas A. It is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. Today's lecture is on Geophysics for Geotechnical Engineers, which will be delivered by Professor Carlos Santamarina, Dr. Andreas Pfaffhuber and Mr. Craig Christensen. Dr. Andreas Pfaffhuber has extensive leadership experience in innovation, research, project management, business development and scientific consulting. Pfaffhuber is the visionary behind Airborne Geointelligence. He introduced Airborne Geophysics to NGI in 2007, initially for resource exploration and later for the unique application in geotechnical projects. Pfaffhuber established the NGI Geosurveys section in 2012 based on a strategic research project. Geosurveys develops, adapts and implements geophysical, remote sensing and GIS methods in NGI's advanced geotechnical projects. For 1 year he contributed with business development to NGI's newly established daughter company in Perth, Australia. Pfaffhuber holds a PhD in Applied Geophysics from Bremen University and an MSc in Applied Geoscience from Technical University Berlin. Just like EMerald Geomodelling, Craig Christensen has a talent for bridging the gaps between seemingly disparate fields within applied geoscience. In his MSc thesis, he combined geophysical measurements and geomorphological observations to analyze patterns in mountain groundwater distribution. Likewise, at both EMerald Geomodelling and NGI, he has led development of geostatistical algorithms that model bedrock topography using both geophysical data and borehole data. Christensen started his career at NGI as a summer intern in 2013 and completed his MSc in Geology and Geophysics at the University of Calgary. He also holds a BSc in Geological Engineering from Queen's University. His talents have been recognized by major academic awards from the National Science and Engineering Research Council of Canada and Queen's University.
Yes, good morning from Oslo. All right, very good. Okay, beautiful. So thank you so much for the opportunity to contribute to this lecture series. We're very happy about that. We have a very, very long and complicated title of our talk, but what we're actually going to talk about, or what we're actually going to focus about, are three main things. And those are, get into the right. Okay, yeah, the three main issues that we're going to cover is they all touch about the right way of doing geophysics in a geotechnical project. And there are three important factors. One of them is timing. What is actually the right time to do your geophysics in a bigger scale geotechnical project? Number two will be how you integrate your geophysics with the other types of data and the other models that you usually work with, and how do you communicate that? And then number three will be how to maintain these models. Sorry, there we go. Yeah, it might be a bit confusing to begin with what we mean with geophysical model maintenance, but by the end of the lecture, it's going to be crystal clear. We're very convinced about that. We hope about that. And there will be a bonus point as well, where we talk a little bit about qualitative, quantitative, direct, indirect savings that you might achieve if you do the geophysics right. So that's the three main parts. We're going to go back to those parts as we go through the talk. And we thought, anyway, we start with some introductions. We thought to introduce ourselves a little bit, but I think that's maybe not necessarily necessary any longer. That has been done very well. You might want to get the faces to the names. I am Andy.
And I'm Craig.
And we will lead you through this show. We would like to introduce you a little bit to EMerald Geomodelling, though. Not now to make this into a commercial, but just to give you a feeling of where we're from and what we're talking about and where our main background is. So EMerald Geomodelling is a spin-out from the Norwegian Geotechnical Institute. It's technology that we have, both Craig and myself and some others, have invented at NGI over the years and brought out of NGI into its own company last year which is Emerald Geomodeling. And what we are all about is combining complex 3D geophysics with geotechnical data to provide something that is meaningful for the geotechnical engineer. So you see, of course, a lot of the things we talk about are very closely related to this. However, what we will talk about and what our arguments are based on is our personal experience. We are looking back at a fair bit of time at NGI. Both of us have worked at NGI before, myself for almost 12 years, and Craig for a while as well, starting already in his student days. So that's a lot of the experience that we have, a lot of the things that we've seen that can go wrong, that are maybe not the ideal way. They do go back to those days at NGI, now at Emerald, and also back to our academic time in Canada and Germany. So that's just as a kind of a baseline to give you the background of where we're coming from. Two more issues to introduce you before we go into all of the different cases and examples to underline these 3 points that we want to make are actually the methods that we're primarily going to talk about. Those were indicated in the title of the lecture. We'll talk about airborne geoscanning and we talk about machine learning. So I'd like to spend a little time on what is airborne geoscanning, and there we can touch a little bit back on the earlier talk today about all the different geophysical methods. Airborne geoscanning is an electromagnetic method, but it's not a georadar method. It's not a wave propagation method as such. Helicopter geoscanning, or in the geophysically correct terminology, airborne electromagnetics, is a time domain electromagnetic system. So what you see there on the slides is a big frame, a big ring with about 30 meters diameter that is hanging under a helicopter. And you have a very strong current in that frame that creates a very strong magnetic field, and then you switch off that current and that electromagnetic impulse diffuses into the ground. So it's not a GPR-like reflection transmissivity way of thinking. It is a diffusion process, and we measure the secondary magnetic field that is being induced by that diffusion on receiver coils as it dissipates over time, as it disappears over time. So that's the electromagnetic measurement we're doing. And then we do standard geophysical inversion modeling and find a resistivity structure that can explain the measurements that we take. So the geophysical models that we talk about, that we use, are resistivity models. 3D cubes of resistivity of an area that we've covered in certain depth intervals and spatially. That's the key geophysical method that we talk about. Resistivity models acquired very, very rapidly with airborne geoscanning. Then to the machine learning and why we need machine learning.
Yeah, so regarding the machine learning, being able to interpret what's in the soil and in the subsurface based on our measurements isn't a straightforward process. First and foremost, there's no one-to-one relationship between a resistivity and a soil type. In other words, for any given resistivity, there can be many different soils or rock types that can correspond to it. Moreover, there's many shortcomings and complications with the inversion process. Unlike what Dr. Santamarina showed earlier, we can't scan the subsurface from all different angles. We only can fly above the earth. And there's lots of things to consider there. If you look in the image up on the top of the screen there, that's an idealized conceptual model of what we might see typically here in Norway. It's basically all the things that we might see in any given survey. It's rather complicated, in fact. What you see is many different rock types, many different sediment types, and they're all colored according to the resistivity that you might expect them to have. But if you were to go out into the field, take measurements, do inversion processing, this is what the result might be. You see that we have rather limited resolution, being such a large instrument. We're able to go, 50, 100, 1,200 meters depth in some cases, but a lot of those boundaries that we see in the idealized conceptual model get smoothed out. And in fact, if you look in the center of the image below that thick clay layer, the real resistivity of the gneiss gets mass settled. So just picking a simple one resistivity to contour the top of bedrock at isn't a straightforward process. So it's for these many reasons that we implement machine learning. Sure, you can get an expert to try and go in, compare the geological maps, pick out based on their experience where that boundary might be. But taking into account all that information is challenging and time consuming. That's why we've focused on machine learning, specifically artificial neural networks, among others. Using a nonlinear method to help us do this interpretation helps mimic what an interpreter would do, taking into a different set of interpretation rules for different areas based on changing geology in different locations.
Right, so that's all we were going to talk about methods, and we're not going to go more into any theory or really complicated maths. If you got any questions about that, you can always come back to us later. Now it's time to get to the 3 key points we want to talk about, starting with timing. Timing may be the most important thing. Why is that so important? Well, after all, we want to change, we want to improve the way how we do things. And when I say now we, I would like to consider us as the geotechnical industry. A lot of the standard methods in geotechnical engineering are very well established, really good, but they always leave, there's always room for improvement, right? So some of the methods actually haven't changed for decades. And unfortunately, that again and again and again still leads to problems at the end of a project. This slide here that you see now, that's the big reports that you get from the big consultants, McKinsey and others, that finds that more than 90% of infrastructure projects worldwide go over budget. To various degrees, depending on the type of infrastructure. And of course, there are a lot of factors that play into that, and not all of them are controlled by geology, obviously not. But they do point out, in many cases as well, that the reason that project managers come up with in the end is, why did you go over budget? Because of unforeseen geological conditions. We hear that just far too often. And that's where the timing aspect comes in, and it's just so important that you make the right decisions in the very beginning. Those of you that have maybe used geophysics in a geotechnical project every now and then, you've maybe also run into the situation that you've tried everything that you know that are your standard tools, and then, oh, there's this geophysics, we can maybe solve it with geophysics. No, we actually couldn't, because you were already so deep into a really complicated problem. Then that was the wrong time to ask geophysics to rescue you. What is shown on the slide here is not necessarily related to that statement, but it's just an illustration about the importance of timing. We see a map here, and we show the different resistivities in that area. And you see there are 2 different classes. There's a very low resistivity in blue, which is shale, and it's actually a particular nasty type of shale here in Norway that poses a big environmental and construction problem if you encounter it. And just 50 meters north of that black line everything is red, and that's limestone. And that black line is a planned road cut, which goes right deep into the problematic material. If you do the geophysics first, if you have that decision-based, that knowledge before you start even planning, you can make the right decision at the very beginning. And we'll dive a little bit more in detail what that can mean in a project.
Yeah, let's take an example from last year. This was a project we did in June 2019. And even before we did more advanced analysis of depth of bedrock, we did simple clustering analysis. So this is the area that we flew, and we did, used just simple k-means clustering to find the 4 main groupings within our resistivity data. And even from this, we could pick apart different categories in our data, everything from outcropping rock, shallow, deep, and very deep sediments. And when you compare that, the relative frequency of these classes in our data versus what was already sampled by boreholes, you can see especially those areas of very deep sediment were grossly undersampled. So in order to get the most accurate picture of what's going on in the subsurface, even this simple preliminary tool can help serve as an input to planning follow-up ground investigations.
So this was a qualitative example where you very quickly can see how heterogeneous is my project area. Where are the different areas that I need to focus on? Now, we can take this a step further. We can actually also look at this quantitatively, and what I mean with that is actual depth to bedrock. In most surface infrastructure projects, that's one of the key parameters that you want to know. As long as you're in an area, as long as you're not in an area with 2 kilometers of sediments and where bedrock is far beyond the reach, proper bedrock. But this here is an example where you see a map that shows the elevation of the bedrock interface. So this is top of rock, elevation of top of rock. We've looked through the sediments. And this is an example of a road project. And again, the typical situation, where is the ideal alignment for this new piece of road? This map here is based on only 3 boreholes. And the airborne geoscanning that we did in that whole area. So everywhere where you see the map, we have the geophysical data integrated with only 3 boreholes that you might already have in your area without even drilling a single hole. And how accurate is that? How much information does that really give you? How much can you trust it? Of course, this is not the truth. It's going to be close to the truth. How close? Well, let's check it out. This is the same bedrock topography map based on more than 1,000 boreholes. And if you interrogate that map very closely, of course, you will see differences. But you also see quite clearly that the major features, the major changes in, for example, the northeast of the area, where the blue potential alignment is in an area where the bedrock is very deep, so where you're building on a lot of soft soil, and the yellow-green-ish alignment is almost an outcropping rock. That was already there just based on 3 boreholes. So again, you do that in the very beginning, and you can skip hundreds and hundreds of those 1,000 boreholes that you see in the map on the right. That's the point that we want to make with the timing. There is also room to do geophysics later in the project, and that of course also relates to the more high resolution methods. If you talk about borehole tomography, these sort of things, of course, those you can't do in the very beginning when you have no idea yet where you actually will need more detailed ground information. But things like airborne geoscanning, the mapping methods, the overview methods, they have an incredible value if they're done at the right time, very, very early. And then when you have all this fantastic data, then the journey of integration and communication starts. And that is just as important. Once you've made that investment to acquire all that data, did you really get the absolute max out of that? And we are talking here, when I say integration, we're talking here about these 2 different worlds of geophysics and geotechnical engineering. There are very few geophysicists that understand geotechnical aspects very well, and there are rather few geotechnical engineers that have the whole spectrum of geophysics. So it's always difficult to combine these 2 worlds, and you have to do that the right way. Combining the best of 2 worlds and not really thinking ahead, we have seen that fail, right? Combining a phone and an email device is not just putting a keyboard on a BlackBerry. You need to think a little bit better. And integration and combining them is one thing, but unfortunately, in a lot of geophysical projects that we see, they aren't even integrated, they're more compared. You've maybe, most of you, or many of you have maybe come across a report every now and then which states or concludes that the geophysical investigations match the boreholes. Well, that's very nice, but what do you really do with that? How do you take the value, the information that was actually produced by a geophysical survey that you get in maybe a PDF report with a nice section with some colors and one or two boreholes drawn in, and that conclusion? How do you work further with that? How do you take that into your geotechnical design software? Complicated, isn't it? And also, in addition to that, the world is, as we all know, 3D. Just looking at a section or at a map just never really tells us everything that we want to know. How do you compare one or two geophysical sections with a whole bunch of boreholes that are scattered all over the place that are in a 3D world? Is really, really difficult. What we see here is actually not just a triangulated borehole, triangulated bedrock topography based on boreholes. What we see here is actually one of these results that we talk about. This is a bedrock interface, again, from an Airborne geoscanning survey, based on also the boreholes, integrated with machine learning, and a triangulated, irregularly triangulated mesh of bedrock topography that justifies the boreholes exactly where they are and the geophysical information in between. This is in 3D. So let's dive a little bit deeper into how does this look in 2D and where are the challenges?
Yes, okay. So this is an example from an earlier project where I'm trying to illustrate the challenges of trying to interpret things in 2D. Doing stuff in 2 dimensions requires you to take into account a lot of the complex information all at once. On the section that you see on screen, some of those boreholes towards the right side of the screen are almost right in plane with the line that we're looking at. But many of those are 20, 40, 80 meters out of plane. And when you have features changing in the direction perpendicular to this section, you're going to get strange 3D effects. So if you see that that hole at around 1,200 meters along the profile, it's hard to know, is that borehole go deeper because there's sloping bedrock in that area? And does it not match up with that boundary between blue and yellow resistivities because of 3D effects? Is there a moraine on top of bedrock which is masking that depth? Having a human interpreter that does this qualitatively, we may not get the right answer. That's what you see on screen with those black dots. Someone who's picked out an interface based on where the stronger contrast was. But if you look at the next slide, this is an example of interpretation where we interpolate resistivity data onto the actual XY locations of those boreholes, use that interpolated resistivity data as the training data, and perform the artificial neural network training. So in this case, we see that resistivity boundary is correlated. It tells us that generally the bedrock topography is flat in this area, but the true value is closer to the borehole, which is out of plane here. So taking into account all of these complexities in the data is important if you want to get a good model that looks like this.
And we just never are able to convey the real value, the real richness of the information that we can get from our analysis, from our data, if we just deliver maps and sections. We humans are 3D people. We are used to a 3D world, and the 3D world is just very difficult to take on paper. So obviously the solution is really to unlock that value in giving the end users access to those 3D models. And end users is maybe the wrong word. I would maybe say stakeholders, every stakeholder, because that is another challenge. Even though we produce superb 3D models with, you know, matching the boreholes and all of that, and giving you all the detail that you can reasonably get out of the data. But these 3D models, they are accessible maybe only to 20% of the people that are involved in a project. They're just highly specialized engineers that work with the 3D planning, with the design, but probably not even the project manager has access to that super specialized software. But the project manager also needs to get that understanding, and all the stakeholders around, and also the public can really benefit from really understanding, oh, why did they put that road there? Why did they put that tunnel there? So I've got an animation here that I don't know how well that goes over the web, but maybe you can see a little bit of it. So it should be starting, yeah. We just have a geological map here. You just see different geological units, and then we dive into the depth. Now we see the different colors of the resistivity model in that whole area. You can see that they're bright, they're dark colors. Now we took a little sugar cube and move it through the 3D model, so you can see all the different interfaces, and you can start to explore and try to understand what's going on there in the geology. Where are the interfaces between the different units? You can combine them with what you see on the surface, or do something like what's happening now, is that you actually just remove everything with a certain signature and just look at one particular unit. So that part of geology that's in the south of that project, we would now focus on, and we only see that. And we, in this project, also see where the planned tunnel is. You can't really see that, it's just a tiny little line, but you can use that to really dive into the world in 3D and see where the geological boundaries are in 3D, and see where they interact with the tunnel, at which chainage of the tunnel the construction method probably has to change because it goes from rock type A to rock type B, that sort of information. If you really get that in 3D, then you can start working with it in 3D and understand it how the humans are wired, understanding it in 3D. So that's just the communication aspect. There is no integration, and in this example, it's really just showing the geophysical properties. The next example is a little bit more advanced. Here we actually also did some quite complex machine learning towards a very particular type of soil, something that is quite an issue in Norway and in other northern countries. It's quick clay, and I'm not going to talk far too detailed about that, but it's a particular type of clay that is very, very valuable to know because it's very hazardous. It has a resistivity signature, but it doesn't have a straightforward resistivity signature because there are many other factors that influence the resistivity. So what we had the chance of doing here is actually taking various borehole methods and also lab sample measurements into one big machine learning exercise, and to extract from that 3D resistivity model the volume that we classified as potentially this type of soil, quick clay. So right now we're still seeing the resistivity model, and we're about to cut into that resistivity model, and only the volume that potentially is quick clay appears. So if you think about doing a stability analysis of that area, having that richness of information where you usually just have probably one or two boreholes for a complete slope is valuable. I guess I don't need to prove that point very much further. So that brings us to the conclusion of point number 2. Integration doesn't mean to just add things and compare them. It really means to integrate them. And I think we need to hurry up soon, a little bit. Coming to our third point, which is model maintenance. And what do we mean with model maintenance? I'm bringing up this 3D model again, how beautiful it is. But we all know that the day after that model has been produced and delivered, it's gonna be outdated. It's gonna be wrong. Because one new borehole was acquired, and it was, of course, not centimeters spot on of the model that you had. And another borehole gets acquired, another outcrop is being found, and so on and so on. And then at some point, all the time, all the resources that you spent in creating that first model is getting less valuable, because you know, yeah, it doesn't really fit any longer, and there's this new borehole, and that's the old borehole, and da-di-da-di-da. If you think back about the map that I showed earlier with the bedrock topography model based on 3 boreholes and based on 1,000 boreholes, this is a sandbox, a test data for us where you can test our methods and investigate them, and we could do that exercise here to see how does the accuracy actually increase over time if we use more and more boreholes. If we build a first bedrock model just on a handful of boreholes and then improve it over time. And of course, it would look like that. And as long as you do that, as long as you do that interpretation frequently, you really, really unlock that value. I'm going to briefly touch on one case from a recent project, also a road project. This is an area along a planned bridge. You see the bridge pillars, and the stippled line was the assumed bedrock at the time of the start of the project. Then we did the airborne geoscanning, produced the first bedrock model based on hardly any boreholes. And that's how the bedrock model looked from the airborne geoscanning. So, a lot of new insights. Some areas with way more sediments than expected, and some the other way around. Based on this, the drilling campaign was conducted. And then after the drilling campaign, the model was updated. Now my mouse went somewhere again. There we go. So there you see now, some of the findings were confirmed, some of the findings were improved, and in the end, you've got a bedrock model that respects everything. And you were, to begin with, able to do your drillings there where they were most important.
Yeah, this is from the same project, a slightly different area, but illustrates this with just a couple map views here. Within the first, we had a handful of boreholes to begin with this project, and then within about 13 days, this is what we produced, a bedrock topography model using the artificial neural networks. But not only do we get prediction of bedrock, we also get measures of uncertainty. How much do our predictions vary between iterations of that neural network? And this is an important and valuable insight to help plan those further drillings. And you can see when we look at the changes map, when we acquired over 80 new boreholes by August 2019, that was 2 months after we flew, you can see there's some major changes concentrated in those high uncertainty areas where we had recommended more boreholes. And that's that is a view of the integration of all these together into a single model. What you see in those colors, that's the resistivity volume. Lighter colors are high resistivity. And you also see boreholes drilled down to the bedrock surface, that grayish surface there. And you see that bedrock surface is also colored by uncertainty. You see it's darkest, i.e. lowest uncertainty close to those boreholes. And those that uncertainty gets greater as you get further away from those control points.
Yes, so now we actually have touched on all 3 points. We talked about the timing, integration, communication, and the model maintenance, what we mean with that. And now the bonus point. Quantity versus quality, or in better terminology, let's talk about the direct savings. One of the probably most common question that we get when we talk about our method, or I think also about geophysics in general, is what do we get out of it? How many dollars can we save? How many boreholes can we save? How many boreholes do we have to take after we've done the geophysics? And there's of course never a straight answer to that. There is not Okay, now you can drill only every 1 kilometer, and before you had to drill every 50 meters. It's not that easy. But if we dive down into back analysis of that model that we looked at just a moment ago, you can make some estimates. You can think that way, especially if you compare the precision that you get from the integrated model with the precision that you would otherwise have, which is just a triangulated model over your boreholes, right? I mean, we all do that. We all know that it's not perfect, but if you don't have anything else, that's all you can do. And the only thing you know is that, yeah, between those two boreholes, the only thing you can do is draw a straight line and hope that it's somehow correct. And that's the blue line. That's if you would just draw straight lines between your boreholes and then compare them with the actual bedrock topography. Then you can get a guesstimate of how many boreholes could you maybe save if you desire a certain accuracy. And if you are in the early phase where you may be comfortable with a limited accuracy, you can save up to a factor of 10 of boreholes if you really want to compare it that way. But it's not maybe the right way of looking at this, because again, remember this. Remember not just the number of boreholes, remember the insight and the understanding that you have at the right time, very, very early in the project. And this is an example, again, from a project Sander talked about before. Here it's really not about how many boreholes that were saved. This here is a cross-section over an area where the planned alignment of that road has changed significantly because of getting that information in the very beginning. On the top right of that section, you see these two little half circles, which were the planned alignment. It was planned to put a tunnel down there, 2 tunnels for a 4-lane road. And the Airborne geoscanning indicated very early that that tunnel was probably in soil and not in rock. It was very, very dangerously close to the expected bedrock interface. So it would have probably been a sediment tunnel or maybe a huge cut into the sediments. And so without even drilling a single hole there, the decision was made in the project very early to move the alignment a fair bit to the west. Still, the plan was to have it rather shallow, just some 20-odd meters under the ground. And that's where the soil investigation started, that's where the borehole started, which also revealed that it was uncomfortably close to the bedrock interface. And then yet a new alignment was made, and now the tunnel is in solid rock and will be good to excavate. Now, having that information at the right time, and not just saving a couple of boreholes, the project estimated that they saved about 30% of the planned boreholes. Okay, that's nice. But by changing that alignment early enough, they expect that they saved about $24 million, because that's what it would have costed to build that road in soft soil. Those are the real savings that we need to think about. And that's the real impact that we can make. Because after all, that's what it should all be about. That's what should be our driving factor when we do geophysics and geotechnics, or generally when we want to innovate, when we want to use new methods, when we want to improve our toolbox, our workflow. We want to avoid the mistakes of the past. Infrastructure is incredibly important. Functioning infrastructure is the backbone of all of our societies, and we all need to contribute to make that happen, make that make it possible to build and maintain that in a sustainable way. And that's what we really want to communicate. Then I think it's just time for us to again say thank you very much. It was a big pleasure. It was a big honor to be invited to give this lecture. I hope we could raise some thoughts, stimulate some thoughts. Then we consider this a success.
Good stuff. And I think we have ample time for questions now.
Craig, I hope you can hear me. I think that was really interesting. Yeah, I would let you have your water. It was a long talk, of course.
Thank you.
I think we have already quite a few questions. We'll take the first question, which comes from Eleonora from EPFL. She has two questions basically. The first is that what kind and how much of data did you need to train the neural network? And if you have to update it locally based, for instance, on the specific underground you would expect it in certain regions of the world?
Yeah, that's a good question. I think if we can go back to those descending curves, that really illustrates that best. Regarding how much you need, well, more is always better. I think the minimum in most cases is, a handful. And so of course, yeah, you can get something acceptable with a small number of holes. You can get something rather good if you pick carefully where you get those ground investigations beforehand. And we always do local calibration. We are trying to develop a model that can, perform well in certain regions of the world where we have experience. But for the time being, the best standard for us is always to have local calibration data.
I think what type of boreholes, it's in most of the cases, it's just bedrock control drillings, and we only take the bedrock coordinate, or the depth to bedrock reading. But that's only for these bedrock topography models. For the more complicated models, we have whatever is available, and well, I guess more than that, whatever has a physical relationship to the property that we want to extract. That's maybe a quite important point to make. Because some people are skeptical towards machine learning, they consider it a black box. And the computing details that are going on within the machine learning, I guess you can to some extent consider them a black box, but it's just maths at the end of the day. But the point I want to make is the important thing to trust the result of your machine learning analysis is that the parameters you take in have a causal relationship to the parameters you want to get out, right? So if you wanna look at the soil type and you use the resistivities and then you use certain aspects that are measured in the drilling, you want to use the parameters that actually have a relationship to that information that you want to extract, because otherwise it's really just a black box and yeah, some numbers in and some numbers out.
Okay, let's take the next question. So this one comes from Louis from Wits University in South Africa. He wanted to inquire about how much area can you cover in a single day, and what is the spatial resolution of an airborne survey?
Yes. Let's touch the spatial resolution first. Remember that helicopter, this time domain helicopter system is quite big. Actually, I'm going to go to the last one. Sure. And it flies about 30 meters above the ground. And the EM induction, how the current is being induced in a sort of a half sphere in the ground, of course, means that one measurement contains information that maybe comes from about a 150-meter diameter circle, in a sense. You get, as you fly along the lines, you get much more measurements along the line. You maybe get, you downsample them at the end to maybe every 30 meters or something like that. So you could say the data has a resolution of 30 meters along the flight lines, but the physics has a wider resolution. That's the data, the inversion, how you process the data also brings some limitations in terms of lateral resolution. But that's a fact of existing helicopter systems. So I love that you asked that question, because that brings me to show the bonus slide that I prepared. What we, of course, are working on now is to shrink this whole world, to bring the helicopter system to a drone system for exactly that very reason, to increase the lateral resolution, because then you can fly lower, you can have a smaller system and therefore higher lateral resolution. So this is changing. Right now, it's still rather coarse, and it also has its limitations for very steep structures. It's best for more or less horizontal structures, or not too steeply dipping structures. So that's the resolution. And in terms of how much can we cover in a day, it's about 20 to 30 square kilometers, I would say, approximately. It very much depends on weather. Basically, it's the standard helicopter flying weather. So it's not the system itself is robust, but if there are low clouds and fog and things like that, the helicopter can't fly. So it's around that. Yeah.
I guess maybe a bit longer in the long summer days here in Norway.
Exactly, that's also a factor, yeah.
One other thing, did you mention vertical resolution?
The vertical resolution is, at the best case, almost as good as ground resistivity measurements, in the best case. But that depends also very much about how the flight conditions were, how the geology actually is in an area which is rather flat, and you have primarily soil. You can fly quite low, you get the best data quality, and then you get pretty good resolution in the inversion. But if you're flying in a very hilly terrain and you more have rock conditions, then the resolution will definitely be limited. So in terms of if you want to have that quantitatively, it actually relates back to that curve. You see the best precision that we converge to is in the order of a few meters.
Yes. Next question.
Okay, let's take the next question. So this one comes from Alex from University of Queensland, Australia. And Alex wanted to ask how the measurements are influenced by groundwater, and do you also use magnetotelluric?
Also a really nice question. So, yeah, there's a quite significant part of the story that I didn't mention in the beginning. Airborne electromagnetics, the method, originally comes from the mining industry. It was developed 60 years ago, something like that. And it was a very qualitative method. It was just looking for the big anomalies, for the big signals from metallic ores. And only about, say, 15 to 20 years ago, it was developed that the hardware and the whole processing and everything was developed significantly further to do exactly what you're asking for, to do groundwater mapping. The system that we use comes out of Denmark and was originally designed to map groundwater resources in Denmark. Almost the whole country of Denmark is covered with these measurements, primarily with the target of mapping aquifers and then mapping clay layers above aquifers and so on. So groundwater has clearly a very, very strong influence. If you are in big, in significant packages of sediments, and you have a dry sand has a completely different resistivity than a wet sand. Also, you will see the differences, whether it's saline intrusion or freshwater, as was shown earlier today. So that's where the method actually comes from. What was the second part of the question?
Magnetotellurics.
Magnetotellurics, yeah. Now we don't do. I mean, EMerald Geomodeling is about the processing and integration of the data. So we could do the same workflow that we do with the helicopter geoscanning data with magnetotelluric data. Just that magnetotelluric has a much lower resolution. That's very good to look very deep, but has rather limited resolution near the surface for geotechnical purposes. But for example, for deep tunnel pre-investigations, there could definitely be value in magnetotelluric data.
Okay, let's take the next one. This one comes from Go from Indonesia, and he wants to ask how high is the device from the ground to get the results?
It's the nominal altitude of the frame is 30 meters above the ground.
Okay.
And then the cable to the helicopter is about 45 meters-ish. So that's how, that's the nominal flight specification. But of course, it's always a question of the terrain and a question of safety. In complex terrains, when you have a lot of very high trees or a lot of very steep valleys and tops, then you would have to fly lower because higher. Thanks. Because you don't want to touch the trees, right? And that again decreases your resolution and your data quality. So it's always a bit of a trade-off between data quality and safety. But nominally, 30 meters.
Next, I think this is the last question. We have one from a practitioner, Priyanka from L&T India. She has 3 questions, but I think you have already answered one question about the presence of water body and its influence. So she has 2 questions effectively. The first question is that, how do you distinguish between the sediments present above the bedrock based on resistivity, whether if it is granular or coarse cohesive? The second question is that, what difference from the outcome point of view between the airborne geophysical surveys and the geophysical surveys that are carried out on the ground itself?
Yeah, okay, let's start with the first question here, specifically about the sediments above bedrock. Sediments above bedrock generally have a wide range of resistivities, and those signals give us a basis for interpreting different soil types. You can see in this idealized section here, we have some regions with sands rather high resistivity, some regions with moraine or very high resistivity, and you have different types of clay. Quick clay is that special type of clay that we map a lot here in Norway. So it's those differences that allow us to interpret and distinguish them. An important point, you can see there are some sediments that can have even higher resistivities than some rock types. So an important point in all the projects that we do, we always try to interpret depth of bedrock first so that we can distinguish each half of that resistivity volume. I've forgotten the second part. Can you repeat the second question?
The comparison with ground geophysics. Are they?
Oh, yeah, I think you can answer that better probably. Yeah.
Yeah, I touched upon it briefly a little bit. The lateral resolution of the airborne measurements is limited, and the ground measurements will always have a higher lateral resolution, so they will pick up more detail maybe in the first 5 meters or so that you won't see in the airborne results. And then, but when I say that, I actually mean I'm comparing airborne geoscanning with ERT, with electrical resistivity tomography ground measurements. That gives you very high resolution. If you would compare it with ground TEM measurements, so actually having the same method then on the helicopter, the differences would probably be not that big, depending again a little bit on the setting. And yeah, if you compare it with other geophysical ground geophysical methods, of course It can be all sorts of correspondence or not correspondence, depending on which method is sensitive to which property.
Yeah. Now, Dr. Santamarina's talk really emphasized today that there's a wide cornucopia of methods available to you, but very few that you can run from a helicopter like this and cover a wide area, get good depth penetration on a single day.
Thanks, Craig. I think we have just one more question. Last question is from Jamaluddin from Malaysia. And he says that the processing of the TAME data can be presented in depth slices. What depth slices were used for your bedrock resistivity map?
All of them.
All of them? Basically, actually, that's not entirely true. You can see in this cross section here, the vertical section, that we don't have, we can't trust data beyond a certain depth. We call that the depth of investigation. I suppose you can't see my mouse pointer.
Yes.
Maybe you can see it. Maybe you can see that now. Anyway, the area of that lower section where it gets transparent, that's what's called the depth of investigation. Generally, a lot of the projects that we work with, bedrocks may be between 0 and 150 meters, so we might use only the upper half of those layers as training to the neural network. And in terms of depth slices that goes into it, well, you can see we often interpolate to a 3D cube. Let me just find that slide. That'll be towards the end. Yeah, one of these. You see, we often interpolate resistivity soundings all throughout our project area, so that we have a resistivity profile at each of those borehole locations individually. So yeah, a simple answer, we basically use as many layers in that model as we can trust as training.
Okay, thank you, Andy and Craig.